teachers, it is now time for your fourth period PD, which will be held in the Media Center. Please bring your laptop. Thank you.
So I know you guys like a step-by-step process, which is why I tried to give you that step-by-step process right here. Because if you know your process and you understand why we're doing that process, it makes a whole lot of sense in the stoichiometry, the math part that we're going to be doing. So in everyday life, there are limiting reagents or things that run out that control how much you can make all the time. I want you to think of an everyday life example where things could run out and stop production or something. Go. All right, Jesus table, give me an example. Loud and proud? Okay, running out of gas in the car, right? So what reaction are we stopping, ladies? We're stopping the combustion of gasoline when we run out of gas. Perfect example. Bennett's table? Okay, running out of oil in the car? All right, that's not like more lubricating the engine and so forth. I don't know the reaction per se, but that definitely can apply. Audio table?
Coal in a fire pit.
Okay, so coal in a fire pit or in a an engine, like a locomotive. Okay, yeah.
Running out of photosynthesis.
Running out of photosynthesis. That would, so you're saying the sun is the limiting reagent, it's gone?
Yeah.
Okay, so the sun burns out, everyday life kind of thing, right? Ian?
The cheese, pepperoni, lettuce, pizza, lunchable.
Oh, that is horrible. Which one runs out first normally?
Always the pepperoni.
Is it? It's a sad day. They should have appropriate ratios in that to make this happen. They don't? How about peanut butter and jelly? What do you normally run out of first?
Peanut butter jelly.
Depends on the person. Okay. If you're me, it's peanut butter. Alright, so Mason's going to make everybody peanut butter and jelly. He's got some slices of jelly. You guys know the slice version. Okay, Mason, come on in. Stand up. He's got some slices of peanut butter, because, you know, some slices. And he's got some nice white bread. Bleached flour. So here we go. And go. Let's go, sir. You guys are the history leaders.
Come on, man.
Come on, let's go.
Let's go.
We have one. One person.
Make some more. You're better than
We're
peanut butter and jelly. You are killing me.
Come on, Mason.
Killing us. We're essentially dying because of you.
I will stop making it.
You made it backwards.
Come on, another one.
Now make one for yourself.
More bread than needed.
Come on, man. Look at us company. You done it. Come on.
We got this, okay. Okay, we have 4 sandwiches. We have 4 sandwiches. What else?
You got this.
What's happening, guys? Guys, we ran out of bread. What is he actually saying in chemistry?
That's a limiting leading agent.
Perfect. Okay, so limiting reagent, and then what are these?
Excess.
Excess, because we have excess, right? Okay, so that is the concept we are learning today. Thanks, Mason. So you only got 4 sandwiches. 4. Gosh. Okay. So that is the concept we're going to learn today, and this is the process we're going to take to make it happen. I'm going to do one example, take it real slow. If you get confused, don't stop me. I'll do another example, and then we can kind of clarify misconceptions or things you need to ask questions about, okay? So we did that. Perfecto. All right, so these are the questions. Things like this will trigger you to think about the question of limiting reagent. First thing you'll notice is that when you read the information, you're given information about iron and information about the other reactant, copper-2 nitrate. So normally we're not given information about both reactants, because then who do you start with, right? Who do you start with the whole process of stoichiometry with? You don't know. So when you see 2 givens, like givens about one reactant and the other reactant, you already know it's limiting reagent problem. Obviously, this says who's the limiting reactant, but in that case, you would have to start with these two identities and proceed. So, first step on your process, what did it say to do? Okay, convert both reactants to moles. All right, so maybe before that we should write the BCE. Okay, write the BCE for this equation or for this reaction. So iron and copper 2 nitrate. What's the most common charge of iron? 3. All right, somebody at Ashley's table get me started. Fe plus. Perfect. Is it 2? Yeah, okay. Malcolm's table pick up.
3 or Cu.
So we're doing a what kind of reaction here? So a metal single replacement. So we're definitely going to be popping copper out of this reaction. And what else do we need? FeNO3, parentheses 3 to show the charge of iron. Everybody, what do I need to balance? What's up here? I got 3 nitrates and 2 nitrates. That doesn't match, right? So what do I need, CJ? 2, 3, 3, 2. Yeah, we're good. Thank you. All right, so we have our balanced chemical equation. That's always our first step because if not, we don't have any ratios to work with and we're kind of stuck, okay? So now we're going to look at the data provided, and we notice that we're given information about both reactants, and we're going to take both of those to moles. First one's pretty easy. How do we take grams to moles? Molar mass, right? Look at that periodic table. My board is going to work today. All right, you guys are human calculators. If you don't have a calculator, go grab one. If not, it's all in your brain. What's the molar mass of iron? I see like 2 periodic tables out. 55.85, thank you. All right, any calculation here? Points, give me one more. 0.064. Okay, so what we have so far is that the iron grams provided gave us 0.0644 moles of iron that we initially have. I'm saying that very specifically. We have this before the whole reaction begins. So we're literally going to write HABE in caps and circle or square that one off so you can see it because the work is going to get kind of long and you don't want to be hunting for numbers that you need and just see a big blob. Okay, so make that big and bold, okay? All right, so now we need to define the moles of the other reactant. So notice I have these 2 quantities provided. How do I get moles from that? That's what we did yesterday. I heard moles over solution or liters of solution and make the...
I was going to say make the milliliters liters.
Yeah, make the milliliters liters, and then when we do that, what do we need to do? Multiply, right. So basically you guys are saying molarity times volume gives us moles. Molarity times volume gives us moles, okay? So molarity is 0.51 moles of copper 2 nitrate on top. Michaela, what's that per 1 liter solution? Good. So the molarity, when we take that 0.51 m, we break it into the fraction that it actually is. It helps us see the units a lot better. Then we're going to multiply that by, what was the volume? What is that in liters? So milliliters, so how many milliliters are in a liter?
Oh wait, no, it's
0.05. So there's 1,000 milliliters in a liter. We're not even close to a liter, right? So we're going to back that thing up 3 times. 1, 2, 3 gives us 2 zeros in the front, and that's our volume in liter form. And that is 0.005 liters. And what is that when you multiply, guys? Somebody at Jaden's table help me out here? Or Amari's table, yeah? 0.00255. Thank you. And we're going to call that moles of what? Copper 2 nitrate. Okay, and this is how much I, what? Have, right? So this is how much I have before the reaction of iron. This is how much I have of the copper 2 nitrate before the reaction. So I'm going to write have there. Okay, this is less just saying like if I had had Mason count out before the reaction, he could be like, yeah, I have like 10 pieces of peanut butter, 8 pieces of jelly, and 9 pieces of bread. That's just us looking to see how much we have to begin with. That's it. But why do you think we need to get both of these to moles? So you can go anywhere. Also, so you can, what are you going to say? Doing this. Look at a ratio, right? Because what are these coefficients representing? What kind of ratios? Mole ratios. They're not gram ratios. They're not atom ratios, right? They're mole ratios. So we have to have this in the right unit to actually be able to use those ratios. Okay, so I see there's a 2 to 3 ratio between these two. So for every 2 moles of iron, I need 3 moles of copper 2 nitrate to fully react everything, and then vice versa. So what I'm truly going to figure out now is like, all right, if I have this much iron, how much copper 2 nitrate do I really need to make all of it react? And vice versa. If I have this much copper 2 nitrate, how much iron do I need to fully react both of those substances? So instead of doing that in my head, because it gets kind of complicated, we're just going to literally multiply by the ratio. So the ratio for this one is going to be how much copper 2 nitrate do I need for every iron? So how much copper 2 nitrate is a 3 to 2 ratio. So I'm going to write that right here, 3 to 2. And I'm going to fill in the blanks with the units, but I just want you to see that's the ratio. So there's 3 moles of copper 2 nitrate needed for every 2 moles of iron, according to this recipe above. We don't even have like even close to 1 mole, so we know this is going to be a relatively small number that we need, but that's the ratio and how they exist. What about this ratio down here? 2 moles of iron over 3 moles of the other. So what do I do from here to here? You're just flipping it because you're talking about the other relationship. It's the same relationship, it's just inverted. So we're going to multiply this one by 2 moles of iron over 3 moles of copper 2 nitrate. Okay, I'm running out of space on mine. Hopefully you have space. We're going to calculate this now, okay? So take your half, multiply by 3 over 2, and then separately half, multiply by 2 over 3. What's the top one?
0.096.
0.096 what? 6 moles of copper 2 nitrate. So notice the moles of iron are counter to each other, so that's canceling. So that's what we're actually going to call that out as moles of copper 2 nitrate. And then the other one, 0.0071 or 17 moles of, notice this moles of copper 2 nitrate cancel these moles of copper 2 nitrate, so that moles of iron exist. Alright, so we're going to label these. We label these have. What do you think we'll label these based on kind of how we were talking? Say again? Need. This is how much we need of the other reactant to fully react all the stuff we have already. So let's call both of these need. And it's really, I guarantee you'll appreciate this. It's so much easier if you could label them up front so that you're not figuring out what's what in the end, okay? Okay, so just like if you were, trying to figure out, okay, I want to make a s'more, but I have 10 chocolates. Well, how many marshmallows would you need for 10 chocolates? 10, because the ratio is 1 to 1, right? So if I only had 5, what would happen to my chocolate? If I only had 5, but I wanted to make 10 s'mores, or I had 10 marshmallows, but what would happen to those 5 chocolates? We would run out, right? We wouldn't have enough to make all the s'mores we wanted. So essentially what you're going to do now is just compare the have and need and the have and need for the 2 of the same reagents. So if I have 0.6, big whopping 0.064 of iron, and I need just little tiny bit, 0.0017. How am I sitting with the iron right now? I'm good, right? I have plenty. I only need a teeny tiny bit, but I have a whole bunch. So that's in excess. So we're going to label this one excess. Okay? But we need to make sure the other one works out, because I'm assuming the other one's a limiting reagent, but let's make sure that it does truly work out mathematically. I have 0.00255 moles of copper 2 nitrate, but how much do I need? A whole heck of a lot more, right? So I only have 0.002, that's nothing. I need like almost 0.1, so what's going to happen to this copper 2 nitrate? It's going to be the limiting reagent, it's going to run out. So we're going to put LR next to that one, so we understand that the copper 2 nitrate is what we're going to run out of. Now we're done. We're done with the whole limiting reagent identification. Now we're ready to actually start the problem. We haven't actually started yet, guys, I know. Truly, the problem is coming in very soon, okay? But now that we've done all this, the problem's a piece of cake. Is the stuff we did 2 days ago, okay? So this is, you don't see very many of these because they are a little lengthy, but they're not so challenging it's just impossible. It's just a process, right? So after we figured out our have, we used our ratios, we figured out our need. We compared the have and need, and how do we figure out who the LR was based on that? Which one had what? Right, the have was less than the need, right? So the LR is copper 2 nitrate because the have was less than the need. That was our thought process, if that helps for you to write that down, okay? Now, on your notes from warm-up, what did it say after we found the LR? What did it say to do? We already did that part. I think it was last step. Use a limiting reagent to solve the rest of the problem. So here's limiting reagent one more time.
Copper 2 nitrate.
Copper 2 nitrate. So the point that really matters on this whole board is the have of the limiting reagent. Like how much you have to start the reaction. So that's the most important number on this board. 0.00255. Okay. So let's look at the problem now. Here's limiting reagent. Copper 2 nitrate. Okay, that one's done. How much copper, what's that mean? Grams of copper will precipitate from this reaction. So that's where you're like, well, you know, if I was just reading this before, I'd be like, oh, which number do I use? But now I know which number to use. I'm going to use the moles of the LR, and I'm going to proceed with that. Okay, so moles of the LR. And I'm going to find grams of copper. So use moles of LR and proceed. So how many moles of LR do we have? That one up there? 0.00255 moles of copper 2 nitrate. Who do I care about in this question? Who am I going to? Good, grams of copper. So that's our question, really. We're in grams of copper. I don't have my ratio available. Can you guys tell me the ratio? Was it? It was 2 to...
2 copper.
What? 2... We're going to copper, guys.
Copper was 3.
Copper?
3 to 3.
3 to 3? Okay, so I assume it's the same number. Just didn't know what the number was. Is it 3 to 3 or 2 to 2? Okay. 3 moles of copper for every 3 moles of copper 2 nitrate. All right, this is a piece of cake from here, right? Give me the grams.
Copper is 63.55.
Okay, so 1 mole of copper is 63.55. Thank you. Grams. Calculate. So we're solving for grams of copper. 0.1 something? 0.162 grams of copper. Let's look at sig figs in a second too, okay? Alright, so we know how to do our stoichiometry once we know where to start. It's the limiting reagent part that has to tell us where to start. That's why that front part's a little bit labor intensive. How many sig figs do I need based on the data provided in this question? 2, right? 0.51 is our limiter of sig figs, so this needs to be recorded to 2 sig figs, which would be what? 0.16 grams of copper. Good. Okay, so that's our answer to the first question. The second question, sorry, I have to keep scrolling. I did not print this out for you. Can I scroll back up? Okay, so the next question is how much of the excess reaction is left over? All right, so if we had, a recipe and we were trying to figure out how much was left over, what do you guys think we mathematically should do, CJ? Have minus need, good. Like you have a whole lot, you only needed a little bit in the reaction. When you subtract those, that should tell you how much is left over, right? It's just math. So we're going to do the have minus need of who? Iron, because iron's my what? Excess, right? So I labeled them down here in my work, but you could have equally labeled them like this is the excess one and this is the LR, so you're not like losing that identification that you worked so hard to figure out. So we're going to do have minus need of iron. Okay, so if you're ever trying to figure out the excess, all you're doing is have minus need, and that will give you leftover. What was the have of iron? It's on your paper. Mine's way up here. 0017 moles of iron. That's the need. This is why we label them. It's just so helpful to go back and look at your work. Okay, so that's the need. What was the have? 0644. Okay, so it's a have of iron, then minus the need of iron gives us 0.0623. 7? So let me just double check this math real fast. This is subtraction. Okay, so we have our moles of iron, but many times if our question is asking about how much do you have left, it's also what unit is it referring to? Grams. So this is grams of excess, grams of the iron. So take me to grams. One mole on the bottom of iron, and what's the molar mass of iron? 55.85 grams of iron. Good. And that gives me what? Say again? 3.50. I think I only need 2 sig figs, so I'm going to stick with that, okay? And that's grams of iron. All right, take a breather for a moment. That was rough. Look back over what we did, and then let's process like the process one more time. Because I know you can do the story. It's the process you need to kind of grasp. Breathe in that oxygen, that bring you some oxygen. Right now it's your limiting reagent.
Yeah, that's what I was just
All right, come back to me. 3, 2, 1. And here we go. What was the key sign that we had to torture ourselves through a limiting reagent problem? When we read the question first, there's got to be a key sign.
The two
Givens for,
moles.
well,
You
they're
have
given
to
for 2 things, right? What are the 2 things the givens are provided for?
volume of
Or iron and copper nitrate. So the 2 givens, I don't want to just say 2 givens because like technically 5 and 0.51 are 2 givens, right? But they're both talking about the same reactant. So I want to make sure you're clear. The data is provided for both reactants, and you're like, crap, this is a limiting reagent problem because I don't know which one to start with. That's your first thought. And then you're like, okay, I'm gonna man up, I'm gonna do it. And so the first step when you figure out that it's limiting reagent is to do what? Get moles, right? And once you get moles, you label them what? Oh, have, right? These are how much we have before the reaction began. So you're like, okay, currently this is how much I have of each reactant. And then how did you go from there? Ratio to get to the need. So then you're like, okay, here's how much I have. Here's how much I really need of both of them. Now you have both of those. Then what do? Hold on. You what? Well, how do you figure out who's excess and how do you figure out who's limiting? Not minus anything yet. You just think. You literally just think. You're like, okay, I have this much. Oh no, I need a whole lot more. What's going to happen? It's limiting. If I'm like, oh, I have this much, and I only need a teeny tiny bit, that's excess. So use logic by comparing these values of have and need. Once you get the logic and you label them LR and excess, why do we do all that? So we can solve the problem with the which part of the which value of the limiting reagent? The moles we have. Right, use them LR moles that we have to solve the rest of the problems. Okay? Because otherwise, we don't know which one's going to help or stop the process. So we have to kind of do that little dance at the front. Okay? Now this one's on you. Go. I'll see where you are in 10 minutes. If I believe in you, we start our homework after this. I have to believe in your abilities, though, before we start homework.
Wait, no, please. Stop. Start with the two. No. Don't even start yet. Okay, we're just what's still easy. Silver one. And silver nitrate is not nitrate elements. So if it does, then would this matter? Then I might don't have it. No, they won't give us a problem. We need food. Silver plus is that all? So we do in front of the 18. You gotta be no, we don't. Oh, yeah. It's the copper. Copper's down to both sides. First time. When 250 grams of copper, we need to convert grams to moles. What's the No, we have to do more there. You could do 400 milliliters. For grams, you just convert. Copper is 63. Calculate. 25, 62. 0.03. There's 3 cases that work.
You guys are talking it out well. Keep going. I'm going to stay 2 steps behind you, and I'll solve the board in about 5.
So molarity times volume, we have this right.
Back to your other one, your steps that you're for warm-up.
Silver nitrate.
Oh, that's right.
And then so what do you multiply by? Yeah, so you multiply the 0.10. You should probably do that. So by that 0.04. Oh, no, it's 24 liters, yeah. And the answer is 0.04. Would that be? So, can you give me order you multiply by rate? Yes. So, in copper, there's one thing of copper for every 2 years old. Is that how it's works? Yeah, because it's asking when do you know when what's the products on? Each one of it's one more copper, yeah. So it would be for every 0.03939. Moles are so like it's 2 over 1 or 1 over 2. So it's still we're solving for yeah, if the copper so that is moles. That's mole of silver. So it's 2 moles. Yeah, so it's you have 0.078. Silver nitrate. Is it silver nitrate? Yeah. Silver nitrate. What is it? 0.078. That's right. And that is and so that is the next one would be 1 over 2. So 0.04. 0.02. That's the common. Yeah, that's the amount of common. 0.02. Now you compare the two, right? Compare. So there's a so now the amount of because we have more excess of copper. Yeah, and we have less. Copper is like excess, and then Reagent is the OR. Yeah, I look at something for like 2 seconds. So once you do this, then we define the LR. How much silver can you just delete it to alright, so once we how much? No, we have to do how much. Well, here, now we have to look at the problem and ask what it's actually needed. How much silver do you are in the reaction? So we need to take the amount of copper minus.
We have our Reagent 3.
Minus the need of copper.
So we're going to start with our photo.
No, we're not trying to
What is our ratio of silver nitrate to copper?
1 to 2. 1 copper for every 2 oxygen.
So 1 mole copper.
No, we're not trying to find copper, we're trying to find silver. You have to do the ratio of silver to silver. Oh, first 2 to 2. Half silver and half silver. And then from there you bring the analysis silver.
You start when you have the 11787.
Yeah.
And then how many grams?
107.87.
So that's just 0.04 times 1. I got 4.81. Let's do 4.3 to 1.
You don't even use it to divide by 2.
Yeah.
4.31.
And then we do the same thing for the others.
For the our is 2.
Yeah.
1, 0.
So just 4.3.
Yeah. That means that we need to draw.
How much of the
Wouldn't it be
reactant
0.020 or
how much of the reactant excess is left over? The reactant excess is constant.
Okay, so then we're going to put the mold of sugar in the
or 10 grams?
How much reactant
It's 0.09. 0.03 moles of copper. That's our excess. Yeah. We subtract that by the difference of copper. So once I get to this, so we have 0.059
What is the more massive
It's 163.
one more. What?
It's after
Alright, give me a thumbs up if you figured out who the LR is. Okay, keep rolling. I'm trying to let some people catch up. Really good conversations though, really good conversations.
So we got
Actual facility 6.64 divided by
I'm keeping my numbers big for now because I don't want rounding error. So don't worry about my sig figs right now. Don't judge me.
As you said that, so percent yield is actual.
so looking at yeah, we always have the actual whatever which one? How many son that's your
The actual faster the
So we just did yesterday. You were here.
How did that? I watched the video last time.
Well, somebody was here.
So if you have the copper,
Go grab your laptops and get done with this. Grab your laptops.
so you determine a lot of
Do this answer. Do this answer. Yes.
Is that the first part?
Yeah, that's one.
I got 4.3. I went to, you're good. You're good. Let's do 6 things.
Where'd you guys mess up?
We didn't forgot about the
We didn't do it right.
Which ratios? These? You guys check your work yet? Check your work yet. Log on. Alright, let's just talk for a hot second and I'm going to keep solving on the board. You guys are processing great, I think. Okay, come back to me. Alright, once we got our halves and we are labeling our ratios so it's really easy to see the mole ratio is between the two reactions is 1 and 2. So if I had 0.03933 moles of copper and I multiply by 2 moles of silver nitrate over 1 mole of copper, that tells me I end up needing 0.0786 moles of silver nitrate. So that's how much I need of silver nitrate due to the fact I have that much copper. Vice versa, I have 0.04 moles of silver nitrate. I need that to react in a 1 to 2 ratio. So 1 to 2 ratio, copper over silver nitrate. And I end up only needing 0.02 moles of copper. So this is where we stop and we have logical discussions with our head. We compare the have of the copper or need, and then the have and need of silver nitrate. And this is my logic. So if it helps to write it out, write it out. If you just want to think it and then write it, you can do that too. Because I have a lot of copper compared to what I need, I'll have excess copper. Because I have a little bit of silver nitrate compared to what I need, because of these numbers, that tells me I'm going to run out. So it's my limiting reagent. So that's the logic step. That's the like over the hurdle, and we're on our way to easiest way geometry from here on. So once you know that silver nitrate's your LR, you use that have number, which was 0.04. We use that to just solve the rest of the problems as needed. Okay. So if you are done with this, I'm going to finish the work up here. Grab your laptop. Okay. You have questions? All the problems at 12. Sorry, guys. You're number 7 or 8 on the problem set. 7 or 8 right now on the problem set.
Are you giving me the answer? 1.2 grams. 1.2 grams. Are we going to eventually understand this or just
Yeah, only do it on math, okay? So unless you want, of course, you can do it. Alright, and come back to me now. You should have had hopefully enough time. It's been like a good 20-something minutes. But these take a long time. That's why you don't see very many, and I'm selectively picking out problem set 12 problems so you're not overwhelmed with the limiting reagent, so that you can just get 1 or 2 more exercises in and you're good. Okay? So as we can see, when the question asks how much silver can be recovered, it's really just asking how many grams of silver are produced from that reaction. Using the half of the LR, we convert to the grams of silver. This is in la land though. This is like if I had a perfect reaction, the limiting reactant worked out exactly the way it should, there was no humidity and stuff in the air, it's literally how much silver I would make, 4.3 grams. So what kind of yield is that? Theoretical yield, right? So that's coming into the question on part 3. So that's the theoretical yield according to how this would work mathematically. And then on part 3, it asks for the percent yield. Well, it told us 3.64 grams of silver is recovered. Well, that's kind of telling you in a lab situation, that's how much you actually recover, what you actually get. So that's your actual yield, which is not that far off from your theoretical yield. So 3.64 grams over 4.3 grams, not bad. 81% yield, I'd totally pick them as a lab partner. So that's what we're working for in the end with percent yield from yesterday. And then, of course, the excess is the subtraction step. Okay, so I'm going to leave that there. And then let's talk. If you don't have a laptop, go ahead and grab one now. 85. I did that from memory. Sorry. Is it 85? 85%. That's 85. So I really don't want to ask you this yet because I know your brain's on fire, but how do you feel on a scale of 1 to 10? Can you accomplish an LR problem like this on a scale of 1 to 10? I'm not saying fast. We're not talking about fast. We're talking about can you accomplish it? Okay, I got most of us on board. I'm happy. I'm going to try to get the rest of us on board here shortly. All right, I will come back to this page in just a second. So listen up. Gosh, guys, we have 35 minutes to do homework. Here we go, okay? So I'm requiring you to do one of these problem set 12 questions right now so that you can, again, kind of prove to me that you know what you're doing. Because problem set 12 is, like, lengthy, and if I can just hand pick 1 or 2 a day that I'm like, yeah, let's try this one, I'm good with that, okay? So what my thoughts are I have the PS right here, but you are going to do 6 through 9 by Friday. But I want you to do right now either 7 or 8. So in your table groups, you can do 7 or 8 right now. After you finish 7 or 8, you can begin your Ed Puzzle video, which the Ed Puzzle video is due tomorrow. But I do want you to take the time to watch it, to answer the questions embedded, and I have provided you a couple of notes already that are pre-printed on your lecture notes. Does anyone have their lecture notes nearby? Thank you. So I have provided you a table with some questions that are on the Ed Puzzle video, so you don't have to write all of that down, okay? All right. So pick out 7 or 8, start that now, and then you can begin Ed Puzzle. I'm not doing it. I'm just trying to make sure that you're confident because if you go smaller and you're like, oh, I know how to do this, it's like better. In my humble opinion, number 8 is faster. In my humble opinion. I wasn't going to tell you that, but Mason's complaining. 8 is easier right now. Mm-hmm.
So, they give you grams, we need for this.
So we take the 80 grams of iron, 3 nitrogen, or just 80 grams of water.
So, what is the amount of mass for iron? Well, we add ours to the iron.
That's a question I said. Yeah, I said, I think before I saw.
It's 241.
That's a house.